Hello everyone, welcome to my channel. Today I want to talk about deep learning basics. Table content is on the screen. First, I will introduce the scenario, predict how much it will rain tomorrow. And second is a data-driven approach. Third is machine learning. Fourth, conclusion and summary. Imagine a farmer who wants to predict how much it will rain tomorrow to make informed decisions. However, he believes that weather forecasts are often inaccurate, so he considers how he can predict how much it will rain tomorrow on his own. The approach comes to his mind using a mathematical model based on scientific theories. As you can see on the screen, there can be ideal gas law, Navier-Stokes equations, thermodynamics primitive equations, but it is too complex for him to apply in predicting how much it will rain tomorrow. The second one, he can predict based on his experience, so data. The farmer has recorded the temperature and humidity data in his notebook for the past 20 years. He wants to use this data to predict tomorrow's weather by finding an exact match to today's temperature and humidity in his past records. However, there is a problem. The number of variables is too small to accurately predict the weather. There are many past records that match today's temperature and humidity, but the results vary, so it makes it difficult to make a clear decision. So he decides to add more variables. Picture. The farmer realizes that weather forecasting is not easy, so he considers adding more variables. But a new problem arises. Now there might be no exact match for today's condition in his past records. The first solution is the nearest neighbor. This method finds the closest matching data by calculating the difference between each variable. There are various ways to implement this method, but I will explain a simple approach. First, calculate the absolute difference for each feature and sum them. As you can see on the screen, I calculate the absolute difference between today's information and the first row of past information. And second, identify the data point with the smallest total difference. And third, use this closest matching data point to make today's weather prediction. This method is called nearest neighbor because it relies on the closest available data, even when an exact match is not found. But a problem with the nearest neighbor is first, it has a lag of generalization. If the difference between today's condition and past data is large, the prediction accuracy decreases. And second, it needs a high computation cost. To predict the precipitation, in these comparing all data points requires a lot of calculations. Second solution is mapping vector to real number. The fundamental challenge is how to transform multiple variables to a single real number. The farmer defines the data as a vector with a shape of one common number of variables, and he realizes that he can convert this vector into a scalar. The method for converting a vector into a scalar is multiply the vector by another vector of shape number of variables, 1. The resulting matrix will have a shape of 1, 1. A 1, 1 matrix can be interpreted as a scalar. Mathematically, this can be expressed as precipitation equals a.25 plus b.high plus c.7.5 plus d.yes plus etc. What this mathematical expression means predicts precipitation by assigning the weight in each of a variable. It is natural that some variables are more important for predicting precipitation, while others are not. Some variables may even have a negative correlation with precipitation, such as yesterday's sunshine. In conclusion, important variables will have large weights. Less useful variables will have small weight, and negatively correlated variables will have negative weight. So in this way, we can solve the problem using data. But how do we determine the weight? We could manually determine the weight, but that would require deep understanding of the relationship between variables and precipitation. This approach feels like going back to solving the problem using mathematical models based on scientific theories. However, we chose to solve the problem using data, so why not use the data to determine the weight instead? The first is the random search. What if we let the computer determine the weight randomly? Computers can generate random numbers extremely fast. The idea is simple. First, randomly assign weights to each variable. Second, evaluate how well these weights perform using the data. Third, choose the best set of weights based on the result. The sheet code is on the screen using Python. Suppose we have the n past data. The past data is named x, and x is n, amplitudes matrix, and past precipitation is our golden number. So it has n, 1 vector. First, we define best weight and minimum loss. Best weight is null and minimum loss is infinity. And we set the end condition like maximum iteration. While end condition, we create a random vector with the shape of amplitudes, 1. And if we dot product between the x and weight, the result will be n, 1 vector. And we evaluate between the predicted precipitation and past precipitation. The evaluator function will make the loss, and loss is less is better. And if the loss is less than minimum loss in now, then we update best weight and minimum loss. In this way, we can update our weight to predict precipitation better. To execute this algorithm, we need to define the evaluator function. The evaluator function measures how well the weights predict precipitation based on past data. Since we are using data, we can compare the predicted precipitation with the actual precipitation from past records. There are various ways to define the evaluator function, but I will explain a simple one. We can measure the absolute difference between the predicted and actual precipitation. Since our goal is to minimize this difference, we need a way to aggregate all differences across the past data points. A straightforward approach is to take the average of these absolute differences. However, instead of using absolute differences, we can use squared differences because they are easier to compute and differentiate mathematically. This evaluation function is known as mean squared error. Using MS error, the sheet code looks like on the screen. Most of the lines are similar in the previous slide, but now the evaluator function is changed into mean squared error. Now we can refine the weight using this algorithm, but there are some challenges. First, it takes a long time to find a good set of weights. Since we are randomly searching for weights, it requires many iterations to get a good result. Second, it's difficult to determine whether the chosen weights are truly the best. Even if we find a good set of weights, we cannot be sure that it is the optimal solution. Are there better methods to solve these problems? Before introducing the better method, I've divided the video into 2 parts so you can take time to think about the better solution. So what about try to think about the better solution? See you in the next one.